take a look at this problem. I know you're thinking, we just did this. Well, let's see, all right? We can reduce this. 6 goes into 6 once, 6 goes into 18 3 times, and now take care of those variables. And we get x, and we get x to the 4th. So we now have, take a look at this. I'll make it bigger because it's really pretty ugly in there. X to the 4th. Oops, almost wrote a 4. Let's fix that. X to the 4th, y squared, all over 3. All right, x to the 4th, y squared, all over 3. Well, that's a perfect square, and that's a perfect square. So we have the square root of x to the 4th is x squared. The square root of y squared is y, and that's all over the square root of 3. But here's the problem. How is this different from the ones we've already done? If you've noticed, I doubt you noticed because you were just excited about this, the fact that we never had a fraction with a radical in the denominator. Now we do. That's a problem. And that's a problem because we are not allowed to have a radical in a denominator. And to be honest, a long time ago the reasoning was because then it would be hard to divide. Now with calculators, sometimes we don't want the radical in the numerator based on higher math or other math. But for us, the rule is no radical in a denominator. So we have to deal with that. We can't just erase it, okay, because then it wouldn't be equivalent to this fraction. So what we have to do is we have to build a fraction that has no radical in the denominator. So this is what I call this. Ready? Nobody else would probably call it this but me. They're allowing me to get away with this here. But here's what I call this. When there's a one term in a denominator, I call this a wannabe. Yes, it's a wannabe. It wants to be perfect. That's what it wants to be. It wants to be perfect. The reason it wants to be perfect is if that was a perfect square, and if it was a cube root, it'd have to be a perfect cube. But if that was a perfect square, then I could take the radical off. Then I wouldn't have a radical in the denominator. So it wants to be perfect. So our job now is the exact opposite of what we just did for 23 slides. Okay? Our job, or 23 lessons, okay? Our job now is to make this an equivalent fraction with a denominator that's perfect. So we have to now use this list to build the fraction. If you remember, it's a fraction. The only thing we're allowed to do to a fraction is to build it or reduce it. We're going to build it because it wants to be. It's what it wants to be. And think of it, it wants to be bigger. Okay, so it's going to be bigger than 3. Okay, so we're going to multiply it. But remember, we have to multiply, whatever we multiply the bottom by, we have to multiply the top by, because we can only multiply by 1. So our job is to figure out what it wants to be. So you're going to start with this list, and now you're actually going to start on the top of that list, this list. And you're going to figure out what that 3 wants to be. But remember, you have to be able to make it that by multiplying. So the 3 has to go into the number without a remainder. Can you make a 3 a 4? Nope, because 3 doesn't go into 4 without a remainder. Can you make it a 9? Yes, you can, okay, because 3 goes into 9 without a remainder. So it wants to be the square root of 9. That's what it wants to be. So now what you do is you say to yourself, why do I have to multiply this to make it the square root of 9? Well, you have to multiply it by the square root of 3, because the square root of 3 times the square root of 3 is the square root of 9. Understand where we got that 9. We had to figure out what this wanted to be. We work off our list, and it's the first number we can make it by multiplying. So it's a 9. What you do to the bottom, you do to the top. Now, remember radicals, outsides with outsides, insides with insides. There's no other radical up there. So this is just x squared y, square root of 3, all over the square root of 9. But now we're happy, because we wanted to make it the square root of 9, and it is. So it is x squared y, square root of 3, all over 3. We are now done because the radical's out of the denominator. And this we don't have to simplify because it can't be. We are done. X squared y, square root of 3, over 3, done deal. That's called a wannabe. We're going to do more. All right. I'm going to probably do this different. I'm going to tell you I'm going to do this different. I look at this and I see I can't reduce. I try to reduce. I can't. One's an inside, one's an outside. We have a radicand and we have just a regular constant term, so I can't reduce. Here's the deal. A lot of people will simplify this. I don't want to do that. If the number was huge, I'd do it. But I don't want to do that because I don't want to simplify and then build and then simplify again. That to me is a waste of my time. So I see that that's not a perfect square, and right away I call that, yes, a wannabe. Okay? So it wants to be perfect. It's a wannabe. So now we have to figure out the smallest number, because if it's smaller, then we don't have to simplify it as much. So I start up here. Now remember, it's a wannabe, so it's what it wants to be like when it grows up. So it's going to be bigger than 32. So we want it bigger than 32, but we want to be able to make it that way by multiplication, because remember, it's a fraction, we're building it. We build it by multiplying. So 36 cannot make 32 a 36. 49, nope. 64, winner, winner. 32 goes into 64 without a remainder. So this wants to be the square root of 64, and I really think it's a good idea to figure out what it wants to be first and write that down. Okay, so now I have to figure out what I have to multiply 32 by to make it 64, and I have to multiply it by 2. So I now have, are you ready? I think this is so cool this way. I like this. Okay, 5 square root of 2 all over the square root of 64. But the square, remember, that's an outside, that's an inside, so it's going to stay that way. Square root of 64 is 8. So my final answer is 5 square root of 2 all over 8. Now I see if I can reduce the outside numbers, but I can't. So I am done. Wannabes, they're awesome. Wannabes. Okay, let's take a look at this one. Well, I have to try to reduce if I can, and I can. Insides with insides, right? So 12 goes into 12 once, 12 goes into 24 2 times. I'm allowed to have a radical on the top as long as it's simplified, okay? So if it wasn't simplified, we'd have to play with that too. All right, square root of 2 all over 14 square root of y. Let's talk about this. The 14 is fine because it's outside. The y, not so fine, okay? And the y has to be perfect. It's not perfect, and that's a problem, right? So here's the deal, what we have to do. Remember what we did before. We took multiples of the index, 2, 4, 6, right? And we took the biggest one that didn't go over. But now we're going to take the first one that goes over. So this is a 1, we want to make it a 2. If that was a 3, we'd want to make it a 4. If that was a 5, we want to make it a 6. Get it? The first one that goes over, okay? And I'll show you why that's going to work. Okay, so this is a wannabe because it's one term. Wannabe, and it wants to be the square root of y squared, okay? So, what do I have to multiply the square root of y by? I have to multiply it by the square root of y, because y times y is your y squared. So insides with insides, and we get the square root of 2y, both inside, and this is 14 square root of y squared. Don't reduce, don't reduce. Don't reduce. If you reduce, you get back here, because we just built it. Okay, don't do that. Okay, so we have, you ready? Square root of 2y over 14y. And now we're done, because 2y cannot be reduced. We cannot break up 2, okay? And y the first is small in the index. You are done. So those are wannabes. Letters are simple. First one that goes over. Remember, we said it's the opposite of simplifying. We have one more to do. All right, let's take a look at this one. This is when I probably would do this. I think it's easier to look at. Remember, this is the same thing. I can't reduce this because my inside numbers don't reduce. So this is a wannabe. This is still one term, remember, because it's attached by multiplication. So it's still a wannabe. So we have to figure out what this sucker wants to be. All right? Wannabe. Okay, first we have to deal with the number, and then we'll deal with the variable. So the number, 12. Okay, well, that's an interesting one. 4, no, it's got to be bigger, so we got to go bigger than 12. No, no, 12, yes, 12 can be 36, can it? So, because 12 times 3 is 36. So, it's the square root of 36. Remember what we said about the exponent. 2, 4, 6. It's the first one that goes over. Don't just double it and say 6. Everybody likes to say that. It's the first one that goes over, so it's x to the 4th. So it wants to be x to the 4th. So you ready? So we have to figure out what this wants, what we have to multiply this by to make it this. Well, we have to, let me use a different color for that so that you can see the difference. We have to multiply 12 times 3, and we have to multiply the x cubed times x. So it's the square root of 3x. Okay? Here we go. We got the square root of 21x over the square root of 36. That doesn't look like a 6 to me. How about to you? 36x to the fourth. 36x to the fourth. Do not reduce. You'll get back to here. Okay? Now, square root of 21x, we have to make sure we cannot simplify that. And the exponent's fine. 21 is fine because we have no perfect square in 21. Okay? We have to make sure we see that too. So this is the square root of 21x all over. Square root of 36 is 6. Square root of x to the fourth is x squared. And you're done. So it's the square root of 21x over 6x squared. Beautiful. You cannot reduce this because one's an inside, one's an outside. So you are done. There are 3 for you to try. All right? So take a shot. Use the list. It's really helpful. And we'll come back and look at those. I think I've never said what we call what we're doing. It was on this in your workbook. What we call this rationalizing the denominator. Since this is not a perfect square, it's an irrational number. Once we make it a perfect square, we have made it a rational number. So it's called rationalizing the denominator, and that's what we do to get rid of that square root or that. Yeah, for us, square root in the denominator. Okay, 50. I can't reduce here because this isn't a radical, so I look at 50. It's a wannabe because it's one term, so we have to figure out what it wants to be. Okay, so the smallest number we can make it. So I'm going to start here, and it's 50. Well, so far I can't, 100. I can make it 100. Okay, 50 times 2. Okay, so I want it to be the square root of 100. So here's what I'm going to do. I have to multiply the bottom by 2, square root of 2, square root of 2. So on the top, I have 12 square root of 2. On the bottom, I have square root of 100. Do not reduce. You'll get back to where you started. And I have 12 square root of 2 all over 10. Now look at that. Look at that. First time we have this, I can reduce. 2 into 10 goes 5. 2 into 10 goes 6 times. Outsides with outsides. Awesome if you saw that. 6 square root of 2 all over 5. Great. Okay? Ready for this guy? All right. I don't have to worry about the 8 because he's outside, but I do have to worry about z to the 7th. I cannot reduce because we have y's and z's. Okay? But this is a wannabe because it's one term. So this is a wannabe. Okay, well, remember what we do for these? We take multiples of 2 of the index. First one that goes over. The first one that goes over is 8. So this wants to be the square root of z to the 8th. Okay, so now we have this. Square root of y over 8 z to the 7th. We have to multiply the bottom by z because it'll give me z to the 8th. So we have to multiply the top by z. And we get the square root of yz all over 8z to the 8th. Almost sounds like we're speaking another language. Okay, so we have the square root of yz all over 8, and the square root of z to the 8th is z to the 4th. And we are done. Awesome. Once you know what it wants to be, it's pretty simple, okay? All right, last one. We have, I'm going to rewrite this, square root of x over the square root of 8y. Okay? Now I can't reduce because there's an x here, a y here. I have to look at both the 8 and the y. I'm going to look at the 8 first. So it's got to be bigger than 8. Can't make it a 9, but I can make it a 16. So it wants to be square root of 16. This is a 1. We're taking multiples of 2, right? We're taking multiples of 2. First one to go over is just 2. So this wants to be the square root of 16y squared. To make it that, I have to multiply by 2y. 2y. So I get, on the top, the square root of 2xy all over the square root of 16y squared, which is the square root of 2xy all over 4y. And I can't reduce because They're not all under a radical, and this is done. These exponents are less than the index, and I can't break down in 2. So that's it. Once you can figure out what it wants to be off this list, I think it's pretty simple. All we're doing is building a fraction and taking something that's irrational and making it rational, calling it rationalizing the denominator. Okay, in the do you remember part of your workbook, it says in 1 and 2, find the product. So would you take those two and multiply them, and then we'll discuss them. Okay, we're going to take a couple of things that you should already know and put it all together here. How does that sound? Oh, you're going, I don't know. Only if I know it does it sound good. Here we go. We have to FOIL this. Binomial times binomial, or just distribute, 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 distribute. Square root of 2 times square root of 2. You should know is 2, but if we want to go the long way, we can. Positive times a positive is a positive 1 the square root of 2. Negative 1 the square root of 2. And negative times a positive is a negative 1. This is 2. Good night. This reduces to 0. Minus 1, and we get 1. 1's our answer for that. That came out to be 1. Okay, let's take a look at this. I'm going to do the same thing. 8 times 8 is 64. A positive times a negative is a negative. 8 square root of x. Outside stays outside. Inside stays inside. Positive 8 times the square root of x. Positive times a negative is a negative. Square root of x times square root of x is square root of x squared. This is 64. Good night. We get minus square root of x squared is x. 64 minus x. Okay, well, what do you call these two? Do you remember? Watch this. First term matches, last term are opposites. First term matches, last term are opposites. Those were called conjugates. These are conjugates. What happens when you multiply conjugates that have radicals inside? What do you notice? The radical goes away. There is no longer a radical on these when you multiply conjugates, because when you square a square root, you get what's inside. When you square a square root, you get what's inside. Okay, so think about that. Okay, so that's what happens when we multiply conjugates. So when thinking about that, let's look at this next question. Okay, take a look at this. What's the problem here? The problem here is, first of all, even if we could reduce, we can't, because even if this was a 10, remember there are terms, so you can't reduce. Second of all, the real big problem is that you have a radical in the denominator. However, it is not a wannabe. Why is it not a wannabe? It's not a wannabe because it's 2 terms. So we have to figure out what we can multiply this binomial by. We have to figure out what we could multiply this binomial by. We have to figure out what we could multiply this binomial by so that the radical goes away. Oh, maybe what we just did. When we multiply conjugates with radicals, the radical goes away. So let's multiply this by the conjugate, okay? The conjugate is same first term and opposite second term. Now, I have to tell you, conjugates here that will get rid of the radical is we always have to make sure it's the radical one. So if you have a number and a radical, for instance, if we had this, square root of y minus 6, if we kept that, no, it would still be okay. Nope. Regress. I regress. Don't worry about it. We're good. We're good. So we multiply by the conjugate because there's 2 terms. So understand this is 2 terms, not a wannabe. 2 terms, 2 terms, not wannabe. Okay, so here's what we have. We have 5 times the quantity, 6 plus the square root of y, over this times this. Now listen, we could multiply this out. We could FOIL it, but what's going to always happen to the middle term? The OI term is going to drop out, because when we multiply conjugates, we could fool. So we're going to fool. First times first. 6 times 6, 36. Negative times a positive negative. Square root of y times the square root of y is the square root of y squared, which is really just y. So this is what we have. 36 minus y. Now this is up to you. You can multiply through or you can leave it just like that. Either way is fine. Multiply through or leave it just like that. If you multiply through, you'll get 30 plus 5 square root of y all over 36 minus y. So either answer is acceptable. So now you know how to rationalize the denominator when there's 1 term, wannabe, or two terms, conjugate. So let's try another one, and then we'll let you do this. Okay, we're rationalizing the denominator again because we can't have this. We cannot reduce this. Don't go crazy because they're terms. Okay, so we have two terms, so we have to use the conjugate. So the conjugate of this, and we're rationalizing the denominator, so it's the conjugate of the denominator. Denominator. Okay, so the conjugate is the square root of 3 minus 1. Whatever you do to the bottom, you do to the top because we're multiplying by 1. Oh, the top is going to be a little bearish to do, but we can do it. I'm going to do the bottom first because it's easier. On the bottom, I'm going to fool. Okay, square root of 3 times square root of 3 is the square root of 9. Positive times a negative is a negative. 1 times 1 is 1. So that's truly just 3 minus 1, or 2. That's the bottom. So the bottom is 2. Let's do the top. You ready? I'm going to have to FOIL the top, or distribute, 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 distribute. Square root of 3 times the square root of 3 is the square root of 9, but the square root of 9 is 3. I'm going to do that here. Minus 1 times the square root of 3, plus 8 times the square root of 3, minus 8. So I have 3 minus 8, which is negative 5. These are like terms. 8 minus 1 is positive 7, square root of 3. That's the top. So we have negative 5 plus 7 square root of 3 all over 2. And that's our answer. And we now have a rational denominator. You're going to say, you have a radical in the numerator. Yes, who cares? We just can't have one in the denominator. So we're good. All right. This is the last two problems that are in your workbook. I want you to take a look at these, try to do them, and then we'll come back and check your answers. Stop the video, go to the workbook, and come back, and we'll do this. Okay, let's take a look at this right now. Two terms, so it's not a wannabe. We're going to have to do the conjugate. So we're going to have to multiply by 3 minus the square root of y. 3 minus the square root of y. If you're not sure why you're doing this, just don't follow me. Ask your instructor. Okay, but it has two terms, so I need the conjugate because the middle term will drop out. So on the top, I'm going to write it like this first, and it's going to be up to you whether you want to distribute or not, but I have that. And on the bottom, I can just fool. 3 times 3 is 9, minus, because a plus times a minus is a minus. Square root of y times square root of y is the square root of y squared, which is just y. So you can keep your answer like that, and we've rationalized the denominator. Or you can distribute and get 18 minus 6 square root of y over 9 minus y. Either answer is acceptable. Okay? Let's take a look at this one. This one's a little harder. It's a little harder because we have two terms, top and bottom. We're not worried about getting the radical out of the numerator, only the denominator. So we're using the conjugate of the denominator. Again, it's not a wannabe because it's two terms, not one. So square root of 3 plus square root of 7. Square root of 3 plus square root of 7, right? Whatever you do to the bottom, you do to the top because it's a fraction and we're building. That's how we build fractions. We're multiplying by a form of 1. And now on the top, we're going to distribute. Okay, so it's hard to get a black cap on a blue marker. It just doesn't work. Okay, so here we go. Square root of 7 times square root of 3 is the square root of 21. Square root of 7 times the square root of 7. Let's talk about that. Square root of 7 times the square root of 7 is the square root of 49, and the square root of 49 is 7. So that's plus 7. Square root of 3 plus 3 times the square root of 3. And finally, plus 3 times the square root of 7. This is ugly. Nothing we can do. None of these can be simplified. Usually this 7 is written last, so I'm going to do that. I'm going to write this as, it doesn't matter what order these are in. If you want, the square root of 21 can stay there. Plus 3 square root of 3 plus 3 square root of 7. Plus 7. The constant term is usually last. That's just the numerator. Now we have to do the denominator. Okay, so we're doing the denominator. Here we go. We're going to fool. Square root of 3 times square root of 3 is square root of 9. Square root of 9 is 3. Square root of 7 A negative times a positive is a negative. Square root of 7 times square root of 7 is the square root of 49, and the square root of 49 is 7. So my final answer, I just wanted to get that out of the way, my final answer is this whole thing over negative 4. So let me erase this so I can get that in there. My final answer, square root of 21 plus 3 square root of 3 plus 3 square root of 7 plus 7 all over negative 4. That is my final answer. My goal was to rationalize the denominator, and I've done that. Looks kind of messy, but I've done that. That's the end of this lesson, the end of this mod. Okay, you've completed elementary algebra.